Let me start off the presentation by asking this question. What is time? Scientists and philosophers struggled for dozens of centuries to understand this problem. They came up with different theories, models, and tools, but it still remained unsolved even until today. We're more familiar with the concept of time as a measurement that goes one way, with defined units such as seconds, days, or years. But clearly that's not all, because otherwise, why sometimes we experience certain moments to pass by slower? And why do we feel like, or at least I do, that September was like yesterday, but in fact there's only 50 days left in 2020? In David Eagleman et al.'s Meaning Symposium, the authors take a psychophysical and neuronal approach to discuss how our brain encodes and decodes information related to time, and what factors influence this process. First, I wanted to talk about two models of timing that are introduced in this symposium. The first model we encounter is called the counter model, proposed in 2004. This model suggests that our brain processes information at a constant rate. So if the rate suddenly goes up because of an unexpected event, we would believe that the time lasts longer, rather than that we processed more information per unit time. The counter model indicates that there is a specific circuit in the brain that keeps track of this rate so that we will experience things at different speeds. One of the other models, the state-dependent network model, rejects the idea that temporal processing is centralized in one area. In contrast, it emphasizes time perception as an intrinsic property that spreads throughout the cortical network. This model presents that the way our neural network encodes time is related to the population of neurons currently firing, so essentially, how active our brain state is at that particular moment. It focuses more on change in the neural network on a sub-second timescale, allowing the brain to accomplish more complex tasks, such as playing an instrument, understanding speech, or even Morse code, which involves processing intricate temporal patterns. Despite different classes of models, most of our current understanding of time perception in the brain comes from psychophysical experiments, where we learn about time distortion, time recalibration, or more generally, how our brain encodes time. Recent studies on time distortion suggest that rapid eye movement, adaptation to moving stimuli, and attention would influence our temporal judgment. This might explain why some athletes report that they perceive their action in slow motion during sports games, since they are often intensively focused when they are trying to hit the ball to the other side. The example of a tennis game could also explain how our brain does the calibration process. As a receiver sees the tennis ball coming towards him, his brain needs time to process this visual information, but still at the same time, the ball keeps traveling in midair. Thus, the location of the tennis ball that the brain tells him is always behind the actual location of the brain in reality. In other words, the tennis player never saw the ball in real time, but with a slight delay of 1/10 of a second. But well-trained tennis player did a profound job of striking the ball. This is because our brain can predict the future position of objects under the condition that the object is respecting Newton's law. That's why people can catch a spinning tennis ball, but never a mosquito, because mosquitoes never fly in a predictable direction. However, temporal calibration sometimes leads to time distortion. In one study, when people are presented with a video of lightning shown in slow motion, they judge the duration of the lightning to be shorter than the actual duration. This is because the brain speeds up our subjective time as a result of our sensory feedback. Determining causality is another way of time calibration, where we keep track of temporal relationship between action and its sensory feedback to understand which event contributes to the production of the other event. A key press experiment is set up to study this topic. Subjects were asked to press a button with a subsequent flash after a short delay. Soon after, the subject would relate the flash as a result of the key press. Interestingly, just by reducing the time interval, so the flash appeared right after they pressed the button, the subject reported that the flash appeared even before they did anything, which is understandable because the latency did not match with their expectation that they built earlier. From a neurobiological perspective, time processing is not dependent on one part of the brain, but distributed throughout the entire organ. while brain imaging studies show that some parts of the brain are related to specific functions that contribute to time perception. For instance, by studying monkeys' brain activity, neurons in the lateral interpretarial area seems to be active when testing monkeys' estimation of the passage of time. So, what can we conclude from time perception about the concept of the self? Even though the entire article seems to discuss how the brain takes an essential role in encoding temporal information, however, I would suggest that, from a neuropsychological view, the self is influenced by both biology and the environment. It's just that neuropsychologists are more interested in the contribution of the biological factors, which is mainly the brain. Our brain receives sensory information from the outside world and then absorbs it using different neural mechanisms. Temporal-related mechanisms in the brain contribute to the processing of temporal order and causality of events, together with other tasks. That is to say, our brain is continuously constructing our unique experience of time as an internal representation of the outside world, resulting from a complex interaction between neurons. Thank you for listening.